Humanity has evolved through various ages, the Stone Age, the Bronze Age, the Iron Age, and now arguably the Silicon Age. What will the next age be? Our next speaker has a 20-year career working on carbon nanotubes, which are potentially the next building block for civilization. Baratunde Cola holds a master's degree in mechanical engineering from Vanderbilt University and a PhD in heat transfer and nanomaterials from Purdue. Dr. Cola is also the founder and CEO of Carbice Corporation, whose mission is to produce multifunctional material solutions from Carbice carbon that set the standard for performance, reliability, and low-cost assembly within the world's most important electronic, energy, and industrial products. Their mission is a critical ingredient to advance humans to a more sustainable existence on Earth and beyond.
All right, thank you, Katie. And thank you, Michael, for inviting me to participate in this, this wonderful exchange this week. So Carbice, I'll jump right into it. I mean, we are an Atlanta-based company that's spun out of Georgia Tech. My goal today will be to give you a flavor of what we're doing and why we're important for the customers that we serve in the space market. But maybe more importantly, just to tell you a little bit about my journey and the journey of this company and how we've grown over the years with various points of support in that process. So I'll start off to say that today we're a team of 12, 14. We're expanding. We have an office headquarters in Atlanta, Georgia. We have an office in London and one in Toulouse, France. And we've assembled a very top team of people that come from the space industry, like Bianca Cefalo, who used to be the director of thermal products at Airbus, who heads our UK office, and Hal Lasky, who comes from the semiconductor industry. And really what we're doing as a company is that we are at this intersection where semiconductors, space, and electronic products have really in many ways become one thing for us. But what you'll hear from me today is just a little bit about the strategy of how do you build a company like this and how investments along the path have been helpful. So myself, I was introduced, this is just my leadership team here, but I want to skip forward to talk a little bit about the mission in the sense of why it's structured the way it is. So our mission really aligns us not only with what's happening today in space, but what needs to happen in the future, but in general around being a critical component for the future of electronics. And when you think about it, this is how Carbice views the world, is that the world on Earth, the world in the universe and through space today depends on electronics. That trend will only increase. And when you think about electronics, the natural byproduct of it is heat. And the heat problem drives complexity and cost in assembling and meeting product goals. And so that's where we're at the center of the future in many ways at Carbice, to set the standard for performance, reliability, and low-cost assembly within these important electronic products that will span everything and every part of human civilization. So it's a big mission. But when you look at the space market, just trying to understand where we fit in, the first thing to really wrap your mind around is that today there's already over $250 million of thermal interfaces orbiting Earth. And the way that we assemble them, if you just look at this floor, there's so many panels and things. So there's many levels in which you have to integrate things. You have to integrate electronic boxes inside of the box that does whatever you need it to do. Then you have to take the box and put it on a panel to radiate things out. And it's just a lot of area, right? The way that people do this and have done this for the past 35 years is to use what's called thermal glue, where you stick on a panel to a surface and you have to wait a few days for it to cure. These surfaces are huge. And if you need to redo a box, you have to use piano wire to scrape through the interface, and it takes a week for you to clean it back up and then reassemble it. It's a very risky, laborious process. This is the main problem, and it exists when you want to build things on Earth, but imagine building things in space or zero gravity environments. You can't use glue. So we solve a problem today in helping people build things at lower costs more efficiently, but we also fill a gap for how we're going to expand infrastructure into the future. And I just have one technical slide I want to show because it's important. I'm gonna skip over the thermal data, but I just want to show you to see this image of what Carbice carbon looks like after a thermal vacuum test of a box integration, and you take it apart. The material looks brand new, and there's a lot of science that goes into that. But if you compare that to things that people have tried in the past 3 decades, they fray and they fall apart. And this is really a central aspect of how do you make the technology integration simple and easy. And that's really what we're about. So as a company today, just to give you a sense of the maturity, we're using all of the interfaces for the Capella Star constellation. Those are in orbit operating. We have 2 geosatellites that are launching this month, actually, where we've been built in for some time. The company has over 20 plus active space projects in the US, Europe, and Japan. And we've been through over 2 years of rigorous qualification. This material actually was the fastest material in history to make it through a qualification process at a big US prime. And through the cycling, vibration, has gotten onto the qualified material list and ready to use on programs. So it's a very mature technology. And from a business side, the customers have seen that this is a tremendous business value add, that by taking out that piano wire glue process that I mentioned to you before, customers are able to save over $500 per square inch of assembled interface. And a typical geosatellite will have sometimes 50,000 square inches of thermal interface. And you think about a Starlink or OneWeb constellation satellite, you're looking at a square meter of thermal interface for each satellite. And we're talking about a future where we're going to be putting hundreds of thousands of these. So this is a big problem in terms of the cost structure for the industry, but also just enabling, because at the end of the day, all the heat that's generating these things have to go through these interfaces to get out for things to operate reliably. So it's a huge program impact for everybody building things in space. And just to give you an example, this is actually one of the pre-ship parts that we sent out for one of the customers. We make things large size, right? This is an example you're seeing of aligned carbon nanotube technology, basically looking like black aluminum foil, basically productized over large areas, being cut into parts and being reproducible. So it's not about the nanotechnology, which is what Carbice really, it's its foundational IP. It's really about how do you take these things and you scale them up and turn them into products. And so that's been a long journey. I'm from Pensacola, Florida, the panhandle military town. I went to Vanderbilt University and I was a walk-on fullback. I can tell you that I never thought about going into space or nanotechnology, but life goes in different directions. In my freshman year, I tore my ACL and I needed to find a way to make money my sophomore year. And so I got introduced to research. So I've been working on carbon nanotubes since I was a sophomore at Vanderbilt in 1999. And it's a very long tenure in this space. I went back to sports, I did some things, but I got injured again and I finished the master's degree still working in this space at Vanderbilt before going to Purdue. And really at Purdue, what I tell people is that it's an interesting story, because you have to really, if you want to support something that is a critical component like this, it has kind of long-term impact on society, you got to find the right path. And my personal background, I did real estate and some other stuff before I got into my PhD, but I wanted to start a business. I wanted the business to be based on science and to be impactful. And that was the strategy at Purdue. And my research was funded by NASA. It was funded by Intel. And in that process, I also got to be a consultant for several startup companies in this area, people making CNC ropes and things for the space elevator. That was a big motivating thing. And I got to see and learn a lot. And when I finished, I went to Georgia Tech. And it was a strategy to go there because I knew that at a place like Georgia Tech in Atlanta, the Advanced Technology Development Center is the oldest university incubator in the country. It kind of flies under the radar, but they have these grant-making programs that they give to the professors. So as soon as I started as a professor in 2009, really several seminal things in the journey of Carbice happened. I won a huge DARPA grant. It was a program called Nanothermal Interface. They funded, I think, 16 teams. I was partnered with Raytheon and Purdue, and was able to develop thermal interfacing solutions to solve this problem that was plaguing, that still today plagues the entire military infrastructure. Two, I was able to get engaged with the Georgia Research Alliance, which was able to give me small commercialization grants to my research lab, so that while I was developing science, at the same time, I could go out and engage with customers and actually start to learn about ways to pull this technology into the market. So that was the journey. Through that journey, I started Carbice in 2011 as an IP holding company, mainly because the manufacturing IP that needed to be developed at Carbice was not really conducive to promoting my academic career, where you're really focused on breakthroughs. So with that process, I then brought on my CTO, and from 2012 to 2016, we won grants, subcontracts for a satellite project with the Air Force, grants on power electronic assemblies with the Army Research Lab, and then National Science Foundation Small Business Research Grant. So several millions of dollars went into developing the core technology manufacturing process, building our team. We had a team of 4 people by 2016. And then we already had projects that were working with customers. That grant we had with Air Force, with a partner, got published, and all of the big aerospace primes started to find it and call us and ask us if this was a technology that was real. And honestly, I didn't want to go into space. I resisted. They called me probably 5 times, and I said no 4 times. Then eventually I took a trip out to the facility to tour it. And this is where I learned about this thermal glue problem. They walked me on the floor. I saw technicians come up to me with cuts on their hands from the piano wire process. I saw people laying on what looked like diving boards, putting paste on. And I said, this is a serious, serious problem. And at that point, that's when we really got engaged in qualifications. And we also then were able to, because of this use case, in addition to the use cases we already knew with semiconductors on Earth, we were able to raise $400,000 in angel money to build pilot production facility. So we took it to the next level and built out this pilot production facility. At the same time, in 2016, Atlanta happens to be a sister city with Toulouse, France. I never even heard of Toulouse before the city of Atlanta told me about this program and said, it sounds pretty good. Let me go Google Toulouse and see what they do. And I said, ooh, they do aerospace. We're interested in that. I think it's a good fit. And so we won this startup exchange and went over to Toulouse. They hosted me in Airbus Business Lab for 2 weeks. Really got entrenched in the culture there. The people in the city were wonderful at hosting us and kind of showing us the ecosystem. And we learned so much. And so that became an important part of our process. And frankly, I would travel back pre-pandemic every quarter to Toulouse just to keep relationships going. Between 2016 and 2017, we had enough paid projects with customers going through qualifications to know that we had a technology that was disruptive. And in 2017, we were able to raise a 1.5 million seed round in order to start really working on our go-to-market strategy, which for us, a lot of it is learning and getting more deeper into the process of getting materials qualified with these customers. And we've been successful with that. I started this presentation kind of sharing with you the success we've had in space. We've had success in semiconductor manufacturing. One of the keys to this story working well is that for all the markets, it doesn't really matter. We don't make anything for space. We make one thing at Carbice, and we're able to use it across different markets. But the space market actually, where there's traditionally been a barrier because it seems like it's an expensive and slow market to get into, we actually turned it in our favor and said, let's use it to grow this materials manufacturing business, because once we spend the time with the proper investments to get qualified, it's going to be a stable customer for years to come. And then we can build a small manufacturing facility, which we have today, capable of serving these customers, improve and mature our manufacturing process. Because of the space market, we've been able to mature our manufacturing 3 times. We're at the 3rd generation reactors, which has de-risked it enough to allow us to raise and close a 15 million Series A, which we did in November. And this is going to be fueling us to next year move into a 20 to 30,000 square foot manufacturing facility that's going to scale up this production, not only for our critical space customers we have today, but for the entire semiconductor industry as we move forward into the future. So that's been the story. It's been a very steady, thoughtful story, but it's also been somewhat serendipitous. And, you know, just like any story where things happen we didn't expect, we took advantage of that. But investments from various sources have been required along the way. And I've always kept a close connection to Georgia Tech, and 90% of our employees are from Georgia Tech. And it's so important to leverage the university system to be able to pull what you need to make a company like this be successful. And so just the last a couple slides here, I mean, it's important that if we want to build a sustainable company serving the space market, you have to have some huge applications on Earth as well. And this has kind of been the fundamental foundation. And this is a highly technical slide, but I mean, the take home is that, you know, there's a lot of value in this material for things like GPUs. This is an AMD GPU, 220 watts. We're showing it compared to POR thermal grease solution. And the connection to space is that when you qualify material, especially a thermal material for something like space, it's the most rigorous qualification that you ever could put a material through. Thermal cycling, reliability. So then when you go down to automotive, you go down to gaming and computing, the reliability factor becomes a brand badge that you wear at honor. And that's what I'm showing here, is that this material is the only material that after thermal cycling and use in these GPU applications, the product gets better. Everything else gets worse. And you know, that heritage comes from designing the material to be rugged from day one. I want to show a quick video because it's important too that it's not all about making better thermal performance. Most of the business you win with a material like this, like I showed in the space market, has to do with revolutionizing the manufacturing process. And so this is the only dry pad material that performs like a liquid. And in addition to that, you can stick it onto a surface simply, so it's able to stay in place with your heatsink supplier, and it can be delivered to your factory pre-installed. Now that's a concept that we also have been working on in the space market. Imagine a future where space panels, you don't have to put thermal glue in the factory. The panel already has Carbice tape on it when it shows up to the factory. And all you have to do is stick your things on and take them off, right? That's a game-changing process that can accelerate build cycle by 200% by having that ability. And so it's things like that that are part of what we're doing for the build process and for the industry in general. But at the end of the day, and the message I want to leave you with, the funding, the investment is important because at the end of the day, science matters. And the differentiation required to bring something like this, to get investors excited about it, requires a very strong scientific differentiation. And that's really what Carbice has. The way we make this material, it is the only viscoelastic material. It's a fancy big word, but all it means is that the material, when you deform it, it always bounces back. And then when you deform it in one spot, it doesn't affect it in other spots. It's like that old Tempur-Pedic commercial where somebody had a wine glass on one side of the mattress and someone jumped on the other side, right? That's what this is. And it's game changing because it's really about the assembly of these products and our visions and our dreams of enabling new things that becomes expensive and complex. And so you're seeing here this deformation, it's unique, and this bounce back. That's what this structure does. And the thermal is a part of it, but it's really a whole package that's being delivered to the customer. And the last slide I have, just because I love carbon nanotubes, you know, I've been working on them since 1999. Any opportunity I get to show an image of a carbon nanotube, I'm going to do it. This is our unique way of doing it with Carbice Carbon. We grow them on both sides of aluminum foil. It's actually recycled aluminum foil. They're vertically aligned and they're well anchored. That was the key processing challenge that we saw. Covalently anchored into the aluminum so that you have a material that uniquely has very high conductivity through the aluminum, and then through the thickness has the high conductivity of these fibers that, as you saw in the previous video, can deform discreetly. So it's almost like a dry liquid to conform around surfaces to make contact. So it's a simple product. It's a simple 3-step manufacturing. It's amenable to continuous processing, to massive batch processing, and it enables us to bring something that on Earth is cost competitive, but in space, both from a performance and cost standpoint, is completely disruptive for builds. So I'll close there. And I hope that was helpful to everybody, and I look forward to questions and a discussion.
Hi, Bara. This is Michael Milling. Good to see you again.
Hey, Mike. Good to see you again.
Yeah, it's good to see the Atlanta skyline in the background there. So one of the questions I wanted to ask was, when you were out raising money for Carbice, one of my favorite companies out there because I love the model, what was your experience talking to investors about the space component of your business? Did they understand it? Was it a turnoff? Was it a challenge to get them to see the value in having two very different market segments, or did they just not care and viewed it as just another industry?
It's a good question, Michael. For the traditional material investors and kind of the traditional investors, the space market was always difficult for them in terms of understanding our complete strategy. Because we're focused on space right now, and I give the reasons clearly why, they would often get confused about the rest of our pipeline and start making assumptions about the product being too expensive or there not being traction in Earth terrestrial semiconductor markets, or how do you translate what you've done there to the other places? So that would be a barrier in communication. And I mean, I think that frankly, only the investors that really already had an interest in space, could I have a conversation and that strategy really resonate with them well. And I think that really speaks to the two investors that kind of brought in this Series A, Downing and Toyota. Both of the directors of the fund, of the VC group, had experience both in space and high performance computing personally. And so it made complete sense to them, and they were super excited about it because of their personal background. But for others, it's a challenge because no matter what I say about we make one thing for every market, it's simple, the thermal interfaces they look the same across all markets. I think people in general are still a little bit hesitant when they hear the word space.
That's our experience as well. I just wanted to see if you'd heard the same thing. I think that as much as we have space in the popular media and science fiction and everything else, it creates this view that space is something that's special and hard. And it's a little bit of a challenge for our industry to overcome that hump. So
you're right, it is. Yeah.
Yeah.
You know what's helped, because I've had to really evolve how I talk about it too. In that slide where I mentioned the fact that there were already over $250 million in thermal interfaces orbiting Earth, that's something that has evolved out of how I've speaking with traditional VCs, just trying to figure out ways to get them to size the market quickly, but then also trying to take that back and explaining that the problem looks the same on Earth, so that they can see the translation. And so it's gotten easier over the years, mainly because we've made progress and I get better at telling the story, but it's still not easy.
I love how you said that. It gets easier over the years.
Yeah.
Bara, can you unshare your slides so we can see the rest of the people here? We have about 20 minutes of Q&A, so I want to kind of kick it off. Charles, do you want to ask your question? I don't want to get into the weeds of carbon nanotube development, but feel free to ask your question.
Yeah, it's just wondering if you've thought of more three-dimensional applications of this technology. Could you brand it helically? Could you form a tapestry? Could it become bigger in one dimension that way?
We have. It's a good question. I mean, so there's always a balance between standardizing the form factor so that you can scale cost effectively versus wanting to expand into different application form factors. So the nice thing about why we use the the aluminum carbon approach we do is that you can form that material and create 3D. You can stamp it, you can bend it around. I have this great example on our LinkedIn page where I take a beer can that I cut in half and I laminate the inside to make a optical cavity, and it looks wonderful, right? It's just the tape pushing it around. So there's limits. I mean, if you have a complex 3-dimensional thing, we don't do that because I think that gets too deep into the processing IP. But it's a good question, and I mean, we've tried to be as thoughtful as possible about making sure that our form factor, which is the foil film base, that we preserve that and then utilize physical properties of the material to their extremes for other things.
Cool. Thank you. Appreciate that. Could you talk a little bit about, look, I think the tech is pretty amazing. No joke. When I was watching your, at the end of this conversation, I want you to point out your website, and I'm going to tell everybody to go and watch some of those videos. The thermal distribution. Thanks, Lila. I appreciate that. The thermal distribution is on video. It's actually pretty astounding. So nice job on that. I want to talk about how this technology moves into industry, and I want to talk about your workforce. How did you get, I think you said you had 14 people, is that right?
Yes.
Yeah. So how did the technology evolve? How did your workforce evolve along the way? You came at it by accident, right? The injury, which led to changing a kind of a life focus, and you were resistant to getting into space at all. So talk me through that evolution, both your staff and the company. What was the evolution process?
Yeah, it's a good conversation, Michael. So, just going back to when I was injured, I always wanted to be in business and be an entrepreneur. I just didn't have a sense of the options available and like what I wanted to do with that. So, before my injury, I thought I would have an engineering consulting firm, like do HVAC. Then I saw nanotechnology, and I was really trying to figure out what that was. But a lot of the talk around nano was always tied around space too. And so I was just trying to figure out what that was for a long time. And even when I was a grad student, I was consulting for these other nano companies. My vision was small for what I could do with this thermal interfacing thing. I thought that maybe I would build a company that would do 10, 20 million in revenue with it. And it was really just because of my limited scope. And so I've been patient. So I think the workforce thing in my mindset has always been to not, to take as much time as I can, as long as I'm able to satisfy the things I need in my life, so that when I go out and I really take that shot, I hit it in the bullseye. Nice. I was uniquely able to do that because of the academic route and kind of going into the university. And what I discovered about myself in the academic route was I discovered my communication gift, if you will, that I was able to reach people and teach and also mentor and understand the type of talent that I would need to build a company and how to diversify that. And I learned those lessons in a research group, in a classroom environment. And so when I recruited my CTO, he'll tell this story. It's funny. I always agreed to be on people's committees that I thought were interesting people. And he was interesting because he used to bother me about making CNTs for him for some thermal capacitor in a chip application. I said, okay, I'll be on your committee. And he did, and I had never seen him speak. And then he gave his presentation at his defense. And I literally chased him down after his defense and brought him into Carbice. Because I said that, you know what? I'm good at materials and I'm good at very simple heat transfer, which is this linear, algebraic stuff for thermal interfaces. This guy's doing like simulations and all this other stuff. He's on the semiconductor roadmap. And as I said, I need this guy on my team. And so that was the first step, that I knew that I'm the materials guy. I'm the kind of, exciting guy talking about the excitement and the vision of the future, but I need somebody like this And I got this fantastic Georgia Tech PhD, Cornell undergrad guy that could be my CTO and drive the application. Because I mean, I think when you think about workforce and building a company, where I saw a lot of the early material companies, have false starts, is that not focusing enough on driving home a particular solution to a particular problem type. And so we, rather than use these aligned carbon nanotubes for everything, electrical, anti-fouling, all these things you could use them for, optical, we focus on thermal. And so this gets into the workforce story. Then I deepened myself into the heat transfer space around this. And my second employee came from a class that I created at Georgia Tech called Nano Engineered Thermal Systems. And he was like one of the students that did really well. And I invited him to do some research with me. And then he came into Carbice, and he's now our director of product at Carbice. So it was really creating the workforce. I decided I was in a unique ability as a professor to not have to go find the university curriculum and do recruiting. If I have time, I can create my own workforce. And I did that. The first 3 employees at Carbice really came out of my research lab in my classes and kind of getting us there. And then once we were 4 people, the next people that joined us, I hired someone who's just a friend of the family, and she kind of came in and became the business jack of all trades, very talented, who's now our controller. And then from there, I think the early part, because the thing is that when you are building a business like this, it's so risky, and we're being so lean with capital. You got to find the right people that can align with your vision and you personally, and just really want to ride that kind of hard life for a little bit. And that's what we did. And then once we got to the angel round, I then turned back to Georgia Tech and found my director, vice president of process and equipment, whom was someone that I knew was as good as me with carbon nanotubes. And he was someone that we used to chat about, knowing each other, interacted for a while. So I pulled someone out of Georgia Tech for that role. And I feel like you have to build the workforce like that. With a material company like this that has IP, you have to build them from your network and people that share in a vision for not only what you're doing as a company, but what you're doing in the community, right? One of the reasons I go for Georgia Tech is because people who are in Georgia Tech, we have a special pride about things that come out of Georgia Tech and make impact on the world out of that. Seed investors was the same. It's hard. I don't know of any material companies that have been successful before us raising money at this level out of Georgia, out of Atlanta or the Southeast. So we went to Tech Square Labs, and Tech Square Labs, Alan and Paul Judge, both Georgia Tech grads, loved getting things in Georgia Tech, but they only invested in software. Right? How did I get them to invest in this? This is where serendipity comes in, is that Paul happened to be building a hardware company, his first ever, called Luma. And he was in China dealing with a heat problem in their manufacturing when I got a hold of them. So it made everything real. And then, so then he's like, well, we don't understand the space, but we like you. We like you, you from Georgia Tech, and this heat problem, we know it's real and it's not going to get any smaller. So that was part of it too. And so the team building and the workforce building for the early stage, all the way to the seed round, really just came out of this ecosystem of research and innovation around Georgia Tech, and then the Georgia Tech brand generally. And then after that, it really started to move into just the fact that it was the right strategy in hindsight, because I wasn't thinking about this clearly when I moved to Georgia, to be in a state that had a huge manufacturing base. In many ways, this gave me confidence as I studied and learned about this more, that we could build a huge manufacturing company here. And I tell people this all the time, that my 5th employee was a technician that we hired that had worked with Suniva, which was a $1 billion solar cell company that came out of Georgia Tech. And we brought him on, and then, we thought, well, maybe we're just lucky, we just found the right type of technician. But even in that process of just going through a proper interview with him, we had 750 applicants to the technician position. Blew my mind, Michael. We have 700, and then because of the applicants, I started looking around and said, "Oh, look at all these companies: Kellogg, Starbucks, making cereal, making carpet." I say, "Oh, wow, we can. All we have to do is like mix a little Georgia Tech with a little bit of what already exists in manufacturing, and we got a high-tech manufacturing environment ready to go."
That's awesome. Well, then that leads me to my very next obvious question. And if anybody has any questions from the audience, just let me know. There's $250 million worth of heat sinks in orbit in space right now, but there's way more than that down here on the ground. So you didn't plan to go to space as your first market, your first target market. What's the transition path from away from space down here on the ground? And when is my computer going to be faster because you dissipate the heat?
Hopefully soon.
Good.
It's a good question.
Thank you. As a consumer who has a lot of digital devices, I really am thinking this problem.
Right before this call, I was looking at a YouTube video of the Sony PlayStation where they use this liquid metal paste, right? And it's just amazing the different things people do that are so messy and expensive. And, again, the value proposition for us in that market is going to be simplicity, right? And consistency, because there's not a single consumer electronic thermal interface solution today that on time zero, when you first open the box, has the same performance that it has after 6 months. They all degrade. And it's because that's just what liquids do. They pump out of the interface and they degrade. So here's the chicken and egg balance with a materials company, and why investors typically, there aren't many investors that have an appetite for materials, is because there's a chicken and egg issue. When you want to get a big account, you have to have big capacity. And very few people are positioned to wait and to invest in that capacity, just because of the way it is. And because of the alternative is always poor performance. And if everybody has it, then you got to convince somebody to move first. So the thing is that we raise this round of funding mainly so that we could build capacity, which we're going to do. We're building a huge facility in Atlanta next year. It'd be 20 to 30,000 square feet. It's going to take us from 500,000 square inches a year of production to over 100 million. So it's going to be huge. And by doing that, then you open yourself up to accounts that are big. But you don't want to do that without having some revenue and some traction. And so space has given us that. Space and some other niche markets we found gave us the ability to make revenue, bring in some business, to show we can execute, to also mature manufacturing so we know what the yields look like and the stats. And then now the transition, I hired Hal Lasky, who is one of the best in the business. And he can take that and scale it to billions. That's what he does. He always jokes with me. He says he doesn't do anything without a B behind it. Billions. So now we have something to translate to him, but it's going to take time, Michael, because you have to have capacity, because these customers move fast. And sometimes they want to ramp from zero revenue to over 100 million revenue with you in 5 months in a semiconductor space.
I mean, I don't want to get into your private business strategy, but I mean, do you have contracts to support that risk, or is it a build it first, they will come strategy, or is it none of my business and you don't want to talk about it publicly, which is a perfectly fine answer?
Yeah, I mean, I think so. The way this market works, here's how I'll answer it, is that you get on the drawing for the parts. It's the same way it works in space. Is it costs so much for someone. I mean, a big prime will cost them for one program over $100,000 to change the drawing. So you work to get on the drawing, and it's not contractual, but at the end of the day, that's what it is, because they spent so much money to get you there. So that's what underwrites our investment, is that we're on the drawings for several things, and we know the size of that.
That makes sense. I'm gonna switch to Charles for one last fast question. We've got 4 minutes till we make our transition to the next speaker. Go ahead, Charles.
Yeah, I just had a quick question about, I was wondering if in cases where
Charles, you need to speak up a little louder, please.
Oh, okay, sorry. In cases where fans are actually very minimally needed in a cooling situation, could you take this technology and do thermal movement in hotspots. Have you thought about that idea? Because that would be a great idea for portable devices that almost don't need a fan.
The short answer is yes. We do thermal straps and things like that. So one of the key aspects that makes this technology universally attractive is that it's an integration technology, meaning that the graphite in the iPhone, because they have to put plastic wrapped around it in order to integrate it, has half the capacity that the material by itself would have. You don't have those losses with our material. So you're able to integrate things and have heat spreading and strapping. So again, it's really, the value is in the manufacturing, whether it be kind of passive cooling like you're mentioning, or active cooling with a lot of fan power or liquid flow.